Hi, my name is Ylva Götberg, and I want to show to you a project that I have recently finished together with my collaborators Valeria Korol, Astrid Lamberts, Thomas Kupfer, Katie Breivik, Bethany Ludwig, and Maria Drout. I work at Carnegie Observatories, but we started this project at the program at KITP last summer, so I would like to extend my thanks to the organizers of the program Gravast 19. Today I want to talk to you about how stars that are stripped in binaries can be LISA sources when they orbit really tightly with compact objects. So I would like you to remember from today that these sources will be low frequency LISA sources that are observable also in the electromagnetic regime, so they are therefore multimessenger sources. Also, with these gravitational wave and electromagnetic observations, we will be able to constrain uncertain binary evolution processes, such as, for example, common envelope evolution, and have a handle on, for example, how many double compact objects can be created. So we are all probably familiar with this evolutionary sequence that is becoming a sort of standard sequence leading to the merger of binary neutron stars, binary black hole, or to some extent double white dwarfs. But since I work on binary evolution, I will take the time to go through this sequence. It starts with two main sequence stars orbiting in a binary. As the most massive star in the system evolves, it swells up and fills its Roche lobe, transferring the envelope to the companion star. What is left is the stripped helium core, or something that I like to refer to as a stripped star. Eventually, that stripped star becomes a compact object. Here, it's visualized as a supernova, but it can also become a white dwarf. If this system remains bound, the mass ratio between the components is often quite large, which will lead to the initiation of a common envelope phase if the system is sufficiently tight. If this binary does not merge during the common envelope phase, what is left is the stripped core of the now second star here, orbiting in a very tight binary with a compact object. In case a gravitational wave radiation tightens this binary, or the stripped star evolves and expands, interaction can occur between the two stars. Eventually, the stripped star will also become a compact object, and if the system remains bound, we have the double compact object systems that may merge and form a different compact object. Usually, when we talk about gravitational waves, there is a lot of focus on this double compact object phase. But today, I would like to focus on a different phase where there is gravitational wave emission, which is when we have this stripped star orbiting in tight orbit with a compact object. So what are these stripped stars? They are typically really hot stars, so between 30 and 100,000 Kelvin. They are small, smaller than a solar radius, or maybe 0.1 solar radius, which will be crucial for understanding them as gravitational wave sources. They cover a range of luminosities from 10 times to 1,000,000 times the solar luminosities, which will also be crucial for understanding that we can detect these sources much easier than many other gravitational wave sources. Since they are the stripped cores of their progenitors, they are helium-rich and hydrogen-poor. So these types of stars are both known as Wolf-Rayet stars and subdwarfs. And they are actually the same type of star. So if we look at a range of mass for these helium stars, in the low mass end, there are the subdwarfs, at the high mass end, there are the Wolf-Rayet stars. In between, binary evolution predicts that there should be an intermediate mass type of stripped star. And that I spend a lot of time working on, but I will not focus very much on them today. Now, since these stripped stars are very small, they fit in very tight orbits. If we compare to other gravitational wave binaries. Black hole binaries and binary neutron stars, they can reach down to sub-second periods, and double white dwarfs to about minutes. But stripped stars orbiting compact objects can reach also really short periods of down to about an hour. So now when we show this with the period frequency range here, you know that the LIGO is suitable for detecting the binary black holes and binary neutron stars, and LISA is definitely going to detect a lot of double white dwarfs. But the significant part of the frequency range that stripped star binaries occupy can also be detectable by LISA. So let's look at where that is in this strain diagram, showing you the frequency on the x-axis and the strain on the y-axis. And here I show only the sensitivity curve of LISA. If we show the same frequency range as before, you can see here that the stripped stars orbiting compact objects will be primarily low frequency sources of gravitational waves. I got really curious about these, so I wanted to make a model for the galactic population of these stripped stars orbiting compact objects. I started assuming this evolutionary sequence leading to the creation of these stripped star binaries. First, I made a model for these first 3 steps using binary evolution models and convolving them with different measured distributions. Then, since there is a sequence of uncertain binary evolution processes, such as the creation of a compact object and the ejection of a common envelope we simply took the simplified approach to assume that about 10% of these systems survive to stage number 7, and that the second stripped star has the same mass as the first stripped star, and that they can occupy a range of periods between the minimum possible period up to 3 times the minimum possible period. We populated the galaxy even in a uniform distribution with these stripped star binaries, which roughly follows the star formation in the Milky Way. As a result, we found about 100,000 of these stripped star binaries. 90,000 of them are orbiting white dwarfs, whilst about 5,000 are orbiting neutron stars. And here I have neglected the stripped stars orbiting black holes, but they should also exist, probably just in fewer number and maybe higher masses. So here we can see the resulting distribution of the Monte Carlo code that we created to investigate this topic. And you can see that the high frequency end here is limited by the size of the star, so how tight the orbit can be, and that is also why as a fraction of them is mass transferring at this stage. The outer edge here is limited by the orbital period, so that's a result of the common envelope ejection. In this particular run, there is about 5 sources that have a signal-to-noise ratio above 5. 4 of them orbit white dwarfs, whilst 1 orbits a neutron star. However, when varying several of these parameters, such as how large a stripped star can be, or what period distribution the common envelope is giving you, the number of detectable stripped stars can vary between 0 up to 100 roughly in our calculations. There are a few observed systems already. First, there is CD-30 here and CTFJ2130. And it is encouraging to see that there is already 2. But another interesting thing is that CTFJ2130 seem to have a higher frequency and therefore be a smaller stripped star than what is allowed in my model. So that could imply that stripped stars indeed can be smaller, and we might have a larger population of detectable stripped star systems. Compared to the double white dwarfs, you can see that the detectable stripped stars occupy primarily a lower frequency regime, as I mentioned previously. So finally, the detected number of these stripped stars with LISA is sensitive to the orbital period, which comes out from the common envelope, and the minimum stellar sizes, which then also includes how the star reacts to mass transfer. Now, as you can see, these two properties are linked to stellar astrophysics and binary stellar evolution. So with LISA, there will be a nice constraint for these processes, especially also since LISA is not limited by extinction, and these sources are likely located in the middle of the stellar disk, of the galactic disk, where the extinction is high. So LISA is going to be launched in quite some time. So if you would like to start to look for them in advance, which I think is something to be encouraged, there are advantageous gravitational wave sources to look for, primarily because they are still undergoing nuclear fusion in their center, so they are really bright sources. Here, compared to double white dwarfs, which have magnitudes about 30 to 40, the stripped star binaries have magnitudes between about 10 to 20, and are therefore much brighter. They are also thought to be deformed because of tidal forces, and as then the binary orbits and the stars is moving in the orbit, you can see more or less of the star, which is leading to a brightness variability. This is the way, this kind of ellipsoidal modulations is the way that Thomas Kupfer and his collaborators could find, for example, CTFJ 2130. We also expect a high radial velocity shift, since the stars are orbiting really fast in the binary, have a very short orbital period. And in 90% of the cases, we expect the radial velocity shift higher than 250 kilometers per second. So that will be exciting for upcoming spectroscopic surveys, for example, such as SDSS-5. However, there is another electromagnetic signal that I think is quite exciting, which is the X-ray signal. If we now look at this cartoon here, where the stripped star is moving in orbit with the compact object, the compact object is actually moving through the stellar wind of the stripped star, and can therefore accrete material as it moves through the wind, which may lead to X-ray emission. And we can calculate or estimate the X-ray luminosity, assuming Bondi-Hoyle-Littleton accretion, in this simple way. So this diagram shows the X-ray luminosity on the y-axis as function of the mass of the stripped star, which is closely linked to the mass loss rate, the wind mass loss rate of the stripped star. And you can see first here the neutron star stripped star systems, and they have X-ray luminosities between like 10 to the 33 to 10 to 36 ergs per second. And in the white dwarf systems, their luminosities are a little bit lower, and most of them will be probably undetectable in the X-rays unless they are accreting. So especially the neutron star systems are sufficiently bright to, for example, be detectable by E Rosita. That we think it's quite exciting, so we started to look for some of these candidates, stripped stars orbiting neutron stars, and I think with collaboration we found some sources. So to finish off, the stripped star binaries should be low frequency. There should be maybe 0 to 100 systems available, and that's sensitive to binary properties. And we expect optical variability, radial velocity shifts, and X-ray emission. Thank you.